Yeah, I think that it's maybe stabilizing. So welcome everyone for today's MINDS seminar. Our speaker today is Reinhard Heckel. Now my colleague at TUM in the electrical engineering and computer engineering department, but he got his PhD 2014 at ETH and also received the ETH Zurich medal for his thesis. Then went on to become a postdoctoral researcher at UC Berkeley and at IBM Research Zurich. And before becoming a Rudolf Mösbauer tenure-track professor at Technical University of Munich, where he is now, he also was for some years at Rice University, which is still his second affiliation now. So I think we are very much looking forward to his insights on untrained neural networks. So Reinhard, the floor is yours.
All right, many thanks. I'm really happy to be here. So what I want to do today is I want to share some of the results we have on using neural networks to do image recovery. So that's a project I've been working on for a few years with some of my collaborators, particularly Mohammed, who is a student at Rice, Paul Hand, and Mahdi Sultanov-Kutabi, who are at Northeastern and at USC. All right, so here's the kind of problems I want to talk about. So I would like to talk about image reconstruction problems. So image reconstruction problems are things like that. Say you have a noisy image as shown here, and your goal is to reconstruct a clean image from this noisy image. So that would be the denoising problem. Or say your goal is to reconstruct a medical image, in this case a knee, from some measurement of a medical scanner. So in this case, that's an MRI scanner. So those are classical signal recovery problems, or signal reconstruction problems, or inverse problems. And they are typically solved, or they are studied since decades, and there are many methods out there. But what has happened in the past few years is that more and more deep networks have been used for these problems. And deep networks perform extremely well on these problems. So here are some examples. So what I'm showing here is an image that I took from General Electric. So that's General Electric CT imaging system. So General Electric builds, amongst other things, CT scanners. And they are using, since 2019, a system that is called True Fidelity. And that's using deep learning to do image reconstruction. And as you can see here, it gives cleaner images than what they have been using before. Another example is MRI. So if you're not familiar with this, there has been a competition that's called the Fast MRI competition. And that's essentially like a challenge to reconstruct images from undersampled MRI measurements. So that's a problem that has classically been solved, or it's known as a compressive sensing problem. And classically that's solved using L1 minimization methods. So what these people have been doing is they built a large data set consisting of measurements and images. And then there was this competition in 2019, and now in 2020 there's another competition where the goal is to do very well using training data. And what this competition has been shown is that neural networks perform like ways better than classical compressive sensing methods. So it's really, no comparison. If you look at these images, the deep learning based ones are super sharp compared to the best total variation or L1 minimization methods. All right, so those two examples and many others have been showing that this works really well for medical imaging problems, but it also works well in consumer electronics. For example, the iPhone has a method that is called diffusion. I don't know exactly what it does, but it uses also machine learning to do computational photography, essentially. So these deep learning systems for imaging are now really used very widely from medical imaging applications to consumer electronics. So the way these things typically work is they train a neural network end-to-end on some large data set. So for example, in the MRI case, the network is trained on mapping a measurement from the MRI scanner to a clean image. And the clean, the data set consists of clean images and undersampled measurements. And then the deep neural networks are essentially like trained end-to-end to perform well on this data set. And the data set is typically very large. In this case, it's a few terabyte. And that's pretty much how all these methods that I mentioned so far work. Or that's how all the best performing methods work. Okay, so what's interesting about this develop is this reliance on data, because the previous generation of methods didn't really rely on data. So L1 minimization doesn't rely on data. Total variation normalization doesn't rely on data. And this reliance on data can be problematic for essentially two reasons. The first reason is, well, it's expensive to collect. But even if you collected it, then there's some concern that deep learning might yield unstable methods for image reconstruction. And there has been a talk about exactly this topic in June in the seminar, where the authors explained various instabilities that trained deep learning methods might have. So here's a concrete example what can happen, but that's a little bit of an extreme example. Like I don't anticipate anything like this happening in in the MRI competition, but that example shows that if you train a data set on a couple of images, then you can have biases like this. So that's the pulse super resolution algorithm, which is a deep learning based super resolution algorithm. And super resolution is one of the most prominent image reconstruction problems. All right. So what's perhaps surprising is that neural networks function extremely well for image reconstruction, even without any training data. So that might come as a surprise, but right now there is already like a large body of evidence showing this for different problems. So this line of work really started in 2018 with this deep image prior paper. I'm going to talk more about this later. And then there were a number of people that showed that this works well for compressive sensing, MRI, dynamic MRI, face imaging, video reconstruction, all sorts of things. And even for, for signal recovery problem beyond image reconstruction, like view synthesis and surface reconstruction and so on. So there are really like tons of examples now where people used neural networks without any training to do very well on inverse problems, on all sorts of inverse problems, even on graphs. So let's start with a concrete example how that can work. So the concrete example is this observation from the deep image prior paper. So the experiment that they performed is as follows. So they took an untrained convolutional network, and they took an autoencoder type network. In particular, they took a UNet. So the UNet is a very standard autoencoder, off-the-shelf autoencoder, and they essentially took the UNet, and then they performed the following experiment. They didn't train the UNet, they just inputted some noise or something else, doesn't really matter. And then as an output, they tried to fit this network to one image only. So essentially they train it on one image. And then they made the following observation. So first they took a clean image. So in this case, I reproduced this experiment, but in this case I took a clean image. And then if you fit this network to the clean image, then what happens is after a few iterations, the network fits this image perfectly. And what's important here is that it fits a clean image after very few iterations of gradient descent. So in this case, there's no stochastic gradient descent, it's really just gradient descent. And then they did the same experiment, but now they fitted noise to this network. So now they have this large unit and they just fit it to represent noise. So now if you do that, you can also represent this noise perfectly if you train long enough, because the network is very over-parameterized. So it can fit any data, any single image. The important part here is that if you fit it to noise, it takes very long to fit the noise compared to fitting the image. And then based on this observation, they said, well, what happens if we fit a noisy image? So in this case, that image is the clean image plus this noise. And now what happens is, if we look at what happens during iterations is that after a few iterations, it has fitted most of the clean image, but it hasn't really fitted the noisy part of the image. And then if we train it long enough, then we also fit then we fit perfectly the noise as well. And essentially then we overfit to the noise, right? So in this case means square error is with respect to the clean image, right? And then what they said as well, based on this observation, what we can do is we can just use this as a denoiser. So we can just take such a network, fit it to a noisy image, and then just stop after a few iterations. And then the hope is that after a few iterations, we get a clean image back. All right, and it turns out that this, just this one experiment essentially works really well as a denoiser. So here's a comparison that just demonstrates this visually. So, so here I took an image, it's some image, I added some noise, and then I looked at, well, how well does the BM3D algorithm perform? So that's like a standard denoising algorithm. And it turns out that this DIP, stands for deep image buyer, works slightly better or the same. So it's hard to say which one works better. They work pretty much on par. All right, and so the conclusion from this experiment is that if you take a neural network, hasn't ever been trained, you fit it to data, then you can solve challenging image recovery problems with kind of state-of-the-art performance. So that's really what this experiment here told us. And that was 2018, so that was the first paper in that direction. And when I started working on this, the following questions really came to mind. So the first question is, well, which architecture enables image recovery? Because it's very much tied to the architecture. Meaning that, they use this UNet, it's a convolutional network, and very particular things about this network enable image recovery like this. For example, if you just take a fully connected network, this won't work. So that's the first question. So which architecture enables image recovery without training? And the second question is, well, why can early stopping of such over-parameterized networks denoise, and how can we explain that theoretically? And the third question is, well, is that a general strategy for solving inverse problems? And, can we really use this to, say, do compressive sensing, MRI, using competitive, or achieving competitive performance? Those are the three things I want to talk about today. So what I would like to start with is the architecture. So which architecture enables image recovery? So the first thing we found is that most of the architecture or most elements of this UNet are completely irrelevant for this observation. And there exists a very simple network that has exactly the same performance and is much simpler and easier to understand. And that network, we call it the deep decoder. It's actually not particularly deep. It's maybe 5 to 10 layers. And what I want to talk about now is just a little bit about this deep decoder network first. So the way we view this network is it's a non-learned deep image model. So it's a prior. And for now, it's a network that maps some low dimensional coefficients to some high dimensional image. So it's very similar to a classical image model, because if you think about sparsity, you could also argue that sparsity essentially maps some low dimensional coefficient space to some high dimensional image space. So it's also a model of exactly the same form. In this case, this map here is nonlinear, and it's parameterized by this neural network. All right, and the network has the following architecture. So it's a convolutional network in the sense that it maps channels to channels. So in this case, this box here corresponds to a number of channels. So if you're not familiar with convolutional networks, just think about it as a matrix essentially. So it's a matrix, and this matrix or these channels are mapped to other channels. And then they are again mapped to other channels and so on. And that's done maybe 5 to 10 times. And afterwards, we just form a linear combination of those channels or columns of this matrix, and that gives the image. And the way how we generate, the way how we go from one set of channels to the other set of channels is to is using these following operations. First, we do 1 times 1 convolutions. So 1 times 1 convolutions are not really convolutions, actually, but that's how deep learning people call this. So it's essentially linear combinations of those channels. So weighted linear combinations. So first we form weighted linear combinations of these channels, and then we perform a convolution with a fixed kernel. And in this case, it's a bilinear kernel, so it just interpolates neighboring pixels. And after that, we apply a ReLU nonlinearity. And that's the only transformation that we perform, and 5 to 10 times. Now, the parameters of this image model are the weights pertaining to this 1 times 1 convolutions. So that's important. In this case, the network doesn't map an input to an image, it maps weights to an image. So that's an important difference in this model. All right, and so that's roughly how this, or that's exactly how this network works. And the way to think about that is it's a subset of a unit. It corresponds to, the unit consists of an encoder and of a decoder. And this corresponds to a subset of the decoder. So essentially of a very simplified version of the decoder. Okay, and so what I want to argue next is that this neural network is a good image model. And the way I would like to convince you that it's a good image model is by arguing that it compresses images well. Because the intuition about an image model is, about an efficient image model is, that it maps some low-dimensional coefficients to a high-dimensional image. For example, if we have a subspace, and if that's a good model for something, then we think about it as mapping some low-dimensional coefficient vector to some high-dimensional space. And in this case, what we did there is, if you take such a network and you make sure that the coefficients, the number of coefficients is 30 times less than the number of pixels you have, that corresponds to a compression factor of 30. So if you represent your image now with the coefficients, you save a factor of 30, right? You compress your data by a factor of 30. And so the comparison here is, I took a number of images from ImageNet. So those are really just like essentially random images from the internet. And then I compared to wavelet thresholding, because wavelet thresholding is what is used in JPEG 2000. So it's a very good baseline for image compression. And now what you see here is that for most images, the performance or the PSNR, the quality that we get is higher if we use, or slightly higher or on par than the performance we get using wavelet compression. So not trying to make advertisement for using this to compress images. So this experiment is really just to demonstrate that this simple network works well at representing images. So it gives you a very concise way to represent an image. And now if you have a very concise way to represent an image, you can, for example, denoise an image. And the reason is, what you can do now is you can just take your representation and fit a noisy image to it. And then the intuition is that it can fit the image, but it can only fit a small portion of the noise. So if you fit it to a noisy image, it will fit the image more or less perfectly, but it won't fit. It will fit a large part of. It won't fit a large part of the noise, and that way you can denoise. So that's like very intuitive. So it's essentially the same as if you conceptually as if you project on a subspace. In this case, you project onto the range of this network. And more generally, if you have such a network, you can solve all sorts of inverse problems, because say you have an inverse problem where the goal is to recover an image from a noisy measurement, then you have some measurement that consists of some measurement process described by a forward model plus some noise. And then if you have such an image model, what you can do is you can just estimate the model parameter by minimizing this loss here. And what that loss does is it takes the measurement and then it fits an image to this measurement that is consistent with the measurement. So we optimize over the parameters of the network such that, you know, the image that the network gives coincides more or less with the measurements that we actually observe. And then we recover our image as what this network here generates. So, you know, like if you have an image model, any image model, then we can solve an inverse problem like that. So one minimization again is very similar, because in that case we do exactly the same, but we minimize over the set of all sparse vectors in a way. All right, so let's see how that works. Let's just start with denoising, because it's arguably the simplest inverse problem, and we will talk about more complicated ones later. So if we use this network and we again do the same comparison, we compare to BM3D and the deep image buyer, then the simple methodology works even slightly better than the deep image buyer. So it gives very good denoising performance. So that demonstrates that, you know, this network really extracts what is critical about this UNet for recovery without training. All right, but now let's go back to our initial observation. So the initial observation was that we took a very over-parameterized network, right? So in this case, the deep decoder is an under-parameterized network. So it's very intuitive what happens. But what if we take this network and we just make it bigger? And bigger, I mean, what if we make it wider? Then we come to a regime where we can represent any image with this network. And then the question is, well, what if we do early stopping? Do we again get like good performance? And it turns out that if we increase the parameters such that this network is over-parameterized, and then we do early stopping, just as we saw before, then we obtain even slightly better performance. I mean, the differences here are really minor. So our goal is more understanding why this works, not so much showing that it works better. All right, and now we are back at this original observation that we have. So if we take the deep decoder, this network, and we fit it to a natural image, then it fits this natural image much faster than it fits noise. And that ultimately enables denoising. So what I want to do next is I want to talk about how we can theoretically understand this phenomena. So what part of the network is it that enables this phenomena? All right, so here, so the way I want to start is like the neural network has all these nonlinearities, right? And these nonlinearities make things complicated. So let's just suppose for a second that the network were linear, and let's see how we can explain a behavior like this using a linear network. And then once we understand that, we go back to the nonlinear network. Okay, so suppose we just have a linear deep decoder. And in this case, linear means it's some matrix J times a vector C. And we call this matrix J because it is a Jacobian of this generator. All right, so now, so some matrix J, and it has some singular values labeled sigma 1 till sigma n, and it has some associated singular vectors, v1 till vn. And so now what happens, so now we can write out the residual after t steps of gradient descent with a constant step size. So that's a very, very standard result. But what this result tells us is that different components of the signal, so different component of the signal would be this. So here y is our signal that we fit. And if we take the inner product with these singular vectors, then we get different components of the signal. And different components of the signal are fitted at different rates. So for example, if some singular value is very large, the component corresponding to the singular value gets fitted very quickly. And if a singular value is very small, the component gets fitted much slower. So here's a concrete numerical example. Suppose we have 5 singular values and they decay as shown here. Then if we look how fast are the corresponding components fitted, then you can see they are fitted at very different rates. So if you early stop at some point, what happens is, so say you stop here. If you stop at 10 iterations, then you almost perfectly fitted this component, but you almost didn't fit at all this other component here, corresponding to this dashed red line. So that's essentially how an effect like this can be understood using just linear least squares. So what happens in linear least squares, different components of the signal get fitted at different rates. And what happens in the neural network is conceptually very similar. So different components of the signal, of the image in that case, get fitted at different rates. So that's really what happens. And we can make that formula as follows. So whenever we want to state a result about denoising or signal recovery in general, we have to start with some signal model. So in this case, our signal model is that X is a smooth signal. And so why do we say a smooth signal? Well, it turns out that natural images can be approximately represented using or they are approximated well by a smooth signal. So for example, if you look at the power spectral density, then it decays very quickly. So it's a reasonably good approximation. All right, so we say that X is a smooth signal, and the way we formalize this is we say that it can be represented as a linear combination of the p lowest frequency trigonometric basis functions. So those basis functions are plotted here. That's the lowest frequency one, and so on. All right, so that's our signal model. So now for simplicity, we consider a two-layer deep decoder. So we consider exactly the network that I showed you before, but we just take a two-layer network one for simplicity. And remember, this network had this convolution operation with with some kernel. So if we go back to this image here, one operation here was this convolution with a fixed kernel. So we have to specify that kernel because the results depend on how this kernel looks like. All right, and what we use in practice is we use a triangular kernel. So a triangular kernel performs a linear interpolation. So it essentially interpolates neighboring pixels. Okay, and so what happens is if we take such a triangular kernel, this kernel induces weights, and the weights are associated with the basis functions. So in this case, they are associated with those basis functions. I think there's a question. Okay, so maybe I'm quickly going to address these questions. So the first question is, in this gradient descent for linear nets, shouldn't you iterate over J and not C? So in this case, we should still operate. We should still optimize over C, because the way we view this linear network is we view this as linear in some parameters. And in this case, all the network is abstracted in this matrix J, and C are the coefficients of the network. So in this case, we optimize over C, and J in a way represents the structure of this linear network. Okay, so the second question is, do you think that these results would hold for tensor data such that stacked videos with 2 spatial and more time dimensions if using a 3D CNN? Yeah, I think the same framework can be used for 3D CNN or also for other networks in principle. So actually, let me come back to this, because I'm also going to talk about the limitations of this approach. And when I come to the limitations of this approach, it's a good point to comment on how it will generalize, but also yeah, what are the limitations of this way of thinking. All right, so. Yeah, please stop me any time if anything's unclear. All right, so I think we understand this I think we understand the Warmup, the linearly squares case. So something very similar happens in the nonlinear case. So we have these kernels, and the kernels induce weights. So the kernel, if we have a different kernel, it changes our network, and that induces weights that are associated with these basis functions. And what's important about these weights is the way how they decay. So here we have a log-log plot. So that tells us that the weights associated with these basis functions, they decay extremely fast. So they become small, like extremely fast. That's essentially what this plot tells us. So that means that, if we have a very similar effect, and it turns out there is a very similar effect, then what happens is like all these elements of the signal are kind of getting fitted one after the other as we iterate a gradient descent. So that's made formalized, or that's formalized here. So suppose we have a noisy observation. So Y is our signal X, and remember X is a smooth signal. So we say that it's like P smooth, so it is well represented by the P smoothest basis functions. And then we just add arbitrary noise to it. And now what happens is, if we look at X, so that's our signal minus the output of the deep decoder at iteration T, then there are two errors here. So the first error is this error in fitting the signal. And here what happens is, if our signal is smooth, then it's well represented by a few of these basis functions. So after a few iterations, the signal part is fitted perfectly. But then there's also an error in fitting the noise. So the longer we iterate, the more of the noise we will fit. And in this case, I choose like just Gaussian noise. So Gaussian noise is equally strong in all directions, pretty much. So what happens then is, like, we iterate for a few iterations, the error in fitting the signal becomes very small, but at the same time, the error of fitting the noise becomes larger, and that's how we get this U-shaped curve. And if we early stop at this point in this example, then we get good denoising performance. So essentially, the theorem describes exactly the behavior of this U-shaped curve. And what it makes precise is, it says, well, if we take a two-layer network, then what happens is, like, the smooth part of the image gets fitted first, and you can see this here as well. It's like very smooth, and the longer we iterate, the more fine components get fitted, and that's essentially how it denoises the signal. All right, and the two assumptions we need for this are as follows. First of all, the network needs to be sufficiently over-parameterized, so it needs to be very wide. And the second condition that we need is, we need to start from a random initialization, and both are pretty important. All right, so let's talk a little bit more about that. So the theorem essentially tells us that in the highly over-parameterized regime, fitting a convolutional generator is equivalent to Fourier thresholding. Because if we look at the theorem holds in the case where the network is very wide. If the network is very wide, then it can actually be well approximated with a linear model. So that's how we formally prove it. And then we study this linear model and we bound the error. So that's how we formally prove it. But conceptually, what happens is, if we make the network very wide, what the network is doing is really doing Fourier thresholding, in the sense that it fits the smooth component first, and then at some point we essentially like threshold. So we don't fit the high frequency components. So that's what's Fourier thresholding. But in practice, this network works much better. So something gets kind of lost in this analysis in a way, unfortunately. But in practice, this way of thinking about what the network does is actually a really good approximation. And that's something we can see from this simulation here. So what I did is I looked at the basis functions and singular values of the Jacobian of the actual network that we use in practice. So remember, the correspondence here is that if the network becomes very wide, then the Jacobian of the network at initialization is a very good approximation to what happens. And the wider it becomes, at some point this approximation becomes more or less exact. Now in practice, what happens is that, you know, the Jacobian at initialization is not exactly the Jacobian after a few steps. So in reality, the singular values change across iterations, and the singular vectors of this Jacobian also change across iterations. And the approximation we essentially make is that they don't change very much. And as you can see here, even in practice, they don't change too much. So those are the singular, you know, functions or vectors, and you can see how they change across iterations. So they definitely do not change very much, but they do change. And same for the singular values, right? So that's essentially what we lose in this approximation, and that's also what we lose in somewhere in this, you know, approximation. That's where really this last boost of performance between Fourier thresholding and what we actually observe comes from. All right, and now let's go back to this question. So the question was like, do you think that these results would also hold for tensor data and so on? So this, you know, you could, for any sort of data, you can have an untrained network. So for example, there are networks that use for 3D data. So there are untrained networks that work for 3D data, and they do work very well. So there's literature on that. And in that, or for videos, for example, so there's a paper where they do this for videos and for video reconstruction. And in this case, yeah, so and in this case, the results would also apply in a very similar way, because now you have a different network, but you can do the same analysis because you can again approximate your network with this linear approximation, and then you can go through the same steps. So in this sense, the results would also apply to that. All right. So then there's a question from Shankar. If I'm correct, a deep decoder is trained with a training set consisting only of one image. So my question is, at test time, can the trained deep decoder be used for any test image? So that's a good question. Thanks for that. So the network is not trained on any image, because like say we do denoising, then we never see an original image, we only see the noisy image. So it's really not trained. It's very similar to, you know, any denoising algorithm. The input is only one image, it's only one measurement. It never sees any original image. So it's really not trained. So therefore, in test time, it can also be used for really any test image in a way. Yeah, but you do need to fit the network. Like every time you use this deep decoder, you need to solve this optimization problem. All right, and then there's a question, is there any hope for theory that is friendly with a wavelet-based image model instead of a Fourier-based image model? I think there is hope, because in this case, if you have convolutions in your network and you have this particular deep decoder structure, then your basis functions are these are essentially these Fourier modes. But if you have a different network, then your corresponding basis functions could be wavelet basis functions. So in that sense, once you change your network, you get different basis functions, and therefore there's hope for theory that is friendly with a wavelet-based image model. So that's a really good question. All right. Okay. So let's move on to compressive sensing with untrained neural networks. So we talked about denoising. So now let's look at compressive sensing. In compressive sensing, something interesting happens. So I think you're all familiar with the compressive sensing problem. Our goal is, you know, we have some measurement Y, some undersampled measurement of a signal X, and here M is smaller than N. Now the way we recover is, as we described before, we fit our network to this undersampled measurement, and then we recover our image as the output of this neural network. So now what happens is, the following. There's no overfitting. So if we do that, we again have a very over-parameterized model, and we minimize this loss. What you can see here is, so 10 to the power of -7, so that's essentially where it converged the network. It's like super small. So essentially we fit our measurement perfectly, but yet the network doesn't overfit at all. So here you see the loss with respect to the image. So when I first did that simulation, I was really surprised because I was always thinking that we also need to do early stopping for compressive sensing. But for compressive sensing, we don't need to do early stopping. So what the network does for compressive sensing is really interesting. Essentially, if you have M measurements, then the signal just fits the best signal it can fit using M measurements. So for example, if you do the same experiment using fewer measurements, then you are also going to recover an image. It's just going to look a little bit worse, but there's still no overfitting. And the way to understand that theoretically is, suppose we can prove this for a Gaussian measurement. So if the network is sufficiently over-parameterized, and again, starting from some random initialization, if we initialize till convergence, so C infinity means if you iterate till convergence, so C infinity means we're running gradient descent until convergence, then the error is bounded by this quantity here. And if we look at this quantity, then we realize if the signal is low frequency. So if the signal lies in the span of, say, M is the number of measurements, so it lies in the span of some constant factor times M, then we essentially perfectly recover it. And if it doesn't lie in the span, then what happens is then we essentially fit the smoothest components of the signal, but we don't really fit the rest. So that's what happens if we do compressive sensing with such a network. All right, so that's why we say a gradient descent finds the smoothest approximation. So that's roughly what this theorem here tells us. Okay, so but the thing that I'm most excited about regarding compressive sensing is that this network works very well in practice for compressive sensing. So here are, like, I'm going to show you two sets of experiments. So one set is by a group led by Michael Lustig, and I'm showing these results just because it's nice to show results from a different group, because it's better if two different groups have verified essentially the same observation that this works very well. And so what this group did is they used exactly the deep decoder that I showed you before, and they used it for MRI reconstruction. And as you can see here, they got significantly better results using the deep decoder than using standard compressive sensing recovery. And that's really that's on real MRI data. So it's not like some toy simulation, and on a real mask that is used in practice. And we also did a lot of experiments on MRI. And here you can see how that performs in practice. So here you have the ground truth. Here you have the decoder. So that's the image that is recovered using the deep decoder. So that's total variation minimization. So that's standard compressive sensing. As you can see, you have really strong artifacts here because it's undersampled by a factor of 4. So that's like pretty strongly undersampled. So here you have none of these artifacts. And here, just for comparison, you have the performance that you get if you use a UNet. So the UNet, in this case, might be a little bit confusing, but in this case, you use a UNet like trained. So the most standard way of doing compressive sensing with MRI using training data is using the UNet. So that's like a baseline method. And as you can see here, it gets performance almost on par with the UNet. It's very hard to distinguish, or it's very hard to say which of these two images are better. And we also verified that experimentally. So those are simulation results by Mohammed, who I mentioned earlier. So here we looked at the fast MRI data set, and we compared the untrained network with a trained neural network. So UNet is a trained network, and total variation is like the untrained baseline. And the metric that is most relevant is this VIF score, because that's what pathologists care about most. And in this score, it even performs slightly better than the UNet. And in the other scores, like structure similarity metric, PSNR, it performs very similar to UNet-based recovery. So I think those results are very interesting because they show that this untrained network can perform on par with a baseline of a trained method. So I'm not saying that it can perform better than the best trained methods. So the best trained methods are better than the UNet. But it shows that it's really not clear, even for the trained networks, how much is contributed from learning from the data and how much is actually contributed from the model itself. So those results also highlight the fact that if you train a network for image recovery, a lot of the performance gains really come from using a very particular architecture. All right. So let me conclude quickly, and then I'm going to address any questions that you might have. So the summary is essentially that untrained convolutional networks can provably regularize inverse problems, and in practice they can work very well. So there's code to reproduce all these results, and the results I presented today are based on these following 4 papers. The first one is really on the architecture, the second 2 are on the theory, and the third one is really on MRI, is really on the practice. All right, with that I would like to thank you very much for your attention.